Welcome everyone to a short video on introducing oxidation numbers or oxidation states in chemistry. Oxidation numbers or oxidation states are used in electrochemistry as a way of keeping track of electrons. The term that's often used is electron bookkeeping. The definition for an oxidation number is this. It's a charge that an atom would have if the electron pairs in a covalent bond belonged entirely to the more electronegative atom. In earlier grades, you may have used oxidation numbers that were listed on the periodic table as a way to determining ionic charge. And on some level, those numbers can be used interchangeably. But more formally, it's simply a way of keeping track of electrons. Even though oxidation states are listed on the periodic table, sometimes they come into conflict with each other. So we have a series of rules to follow to help us determine the oxidation states of individual atoms within a compound. And note that I will use the term oxidation number and oxidation state interchangeably for the purposes of this course. So the first rule, the oxidation number of an atom in its pure elemental or molecular state is 0. So the oxidation state of magnesium, molecular oxygen, molecular hydrogen, aluminum, they're all 0. If we have a monoatomic ion, which just means an ion which just consists of one particle, so not polyatomic, its oxidation number is going to be equal to its ionic charge. So if we have a magnesium 2 plus ion, its oxidation state is 2 plus. Fluorine, the fluoride ion, the oxidation state, -1. Our next rule has to do with the relationship between the individual oxidation states and the charge or lack of charge of a molecule. The sum of all the oxidation states in some sort of compound which has more than one atom is equal to the net charge of that compound. So for example, H2O does not have a charge. So the sum of the oxidation states of the hydrogen and oxygen must equal to 0. For the nitrate ion, which has a 1 minus charge, the sum of the oxidation states between the nitrogen and the oxygens must sum up to -1. And finally, there are some conventions that we tend to follow here in terms of if there's a conflict, which element gets preference. And this table here lists those different preferences. So for example, the halogens, they all have an oxidation state of 1. But if we have a conflict between a fluorine and a bromine, the fluorine will be given the -1, and we'll figure out the chlorine after that. Hydrogen is always given a +1 unless it's in a metal hydride. So some metal just bonded to hydrogen. Then the hydrogen gets the -1. And then finally, oxygen always has an oxidation state of -2 unless the oxygen is part of a peroxide, for example, hydrogen peroxide, and then the oxygen has a -1. Those are the rules, but those rules are best seen as we go through examples. So let's do a few examples to see how these rules get put into play. Now let's go through some examples to see these rules in play. What we want to be doing here is to determine the oxidation numbers of all the atoms in a compound. Let's start with the nitrogen dioxide on the left. If I see oxygen in the compound, I'm going to start there. So I'm going to apply the -2 to the oxygen. Now there's 2 oxygens in the compound, so that means in total we have a -4 oxidation number. Now I'm going to apply the rule that the sum of the oxidation numbers of all the atoms in the compound must be equal to the charge on that compound. There's no charge on the nitrogen dioxide, so that must mean the nitrogen, and there's only one of them, must have a +4 charge. So the +4 charge on the nitrogen and then 2 oxygens, each with a -2 oxidation state, and then we have no overall charge. Let's now look at the sodium nitrate compound. When I have more than 2 atoms in the compound, I'm going to assign oxidation numbers on either end and then work my way into the middle. Okay? So once again, the oxygen is a -2, and there's 3 oxygens. So the sum of the oxygens, we're now at a -6. And I'm subbing them up because I know that we're going to need to balance out the charges. Sodium, being a group 1 metal, always has an oxidation state of +1. So here I have a -6 plus 1. So in total, if I sum those, I'm at -5. And that means the one nitrogen must have a +5 oxidation state, so that the sum of the oxidation states of all the atoms in the compound is equal to the element or the compound charge, which is 0 here. So we see here nitrogen, depending on how it's bonded and what it's bonded with, will have a different oxidation state. Let's look at one more example. The copper 2 phosphate compound. Once again, I'm going to start on the right-hand side with the oxygen, because I know oxygen will be a -2. Now, in this compound, there are 8 oxygen atoms. So that means their sum is going to be -16. Then I'm going to go over to my metal, and I see from the right-hand side here that this is the copper 2 ion. So its oxidation state will be 2+, and there's 3 of them. So in total, we are at 6+ now. I know that in this neutral compound, the sum of all the oxidation states must be equal to 0. So I have a total of +6 on the left, -16 on the right. So that means I'm going to need, from the phosphates, +10 to balance this out. In the compound, there are 2 phosphate atoms. So that means that the oxidation state on phosphate is +5. 2 times +5 gives me my +10, and that will balance out the charges. The best way to get proficient at assigning oxidation numbers is simply to practice. Just go through lists of compounds and practice assigning those oxidation numbers.